Hello everyone, this is Dr. Chen. We will discuss chapter 2 in this video and will be focused on explaining concepts in 1D motion. So we'll be focused on motion in one dimension. So let's start with position and displacement. And to discuss position and displacement, first of all, we need to define a coordinate system. And our coordinate system should have a 0. And it should have a unitness, which in this case give us, in this graph, this length give us 10 meter. And then we need to have a direction of positive. So from 0 to the right is positive. From 0 to the left is negative. And then we have, if we have a car start at position A, which is at 30 centimeter, so this is the position of the car, right? So after you define the coordinate system, the position of the car is just the reading on the coordinate system. It gives us the position of the car. And then the car moves from A to B, and then to C to D, E, and F. Then what will be displacement? So displacement is defined as your final position subtract initial position. And this three short sign, it looks like equal, but there is one more than equal. It means define. So we have delta x, which is displacement, defined as final position subtract initial position. The SCI unit for position is meter. So you have a length subtract length, meter subtract meter, still give you meter. Now let's look at the moving of the car from position A to position B. The coordinate of position A, which is a starting position, right? We call it initial position is 30 centimeter. Final position is 52 meter. Initial position is 30 meter. Final position is 52 meter. What would be the displacement? So by definition, displacement is final position subtract the initial position. My final position is 52 meter. My initial position is 30 meter. So 52 subtract 30 meter give you 22 meter. So the displacement for this movement is 22 meter. Now we look at the movement from C to F. So initial position xi, initial position C, which is 38 meter, and the car eventually stopped at position F with position negative 53 meter. So by definition, displacement equals final position subtract initial position, and the final position is negative 53 meter. Initial position is 38 meter. Up there everything together, we find the displacement from C to F is negative 91 meter. Now we put it together. What is the total displacement? The car move from A to B, and then from B to C, from C to D, and keep going to F. So by definition, displacement is final position subtract the initial position, which is negative 53 meters subtract 30 meter, should be negative 83 meters. So from A to F, the total displacement is negative 83 meters. And on the other hand, so this is by definition the displacement, right? So we want to ask what's the distance the car traveled from A to B and then to C to F. So the car traveled from A to B. A is 30 meter, B is 52 meter. So from A to B, the distance is 22 meter, and then the car moved from B all the way to F. B should be 52 meter. So the distance from B to F, so let's call this one D1, is from A to B, and then from B to F, the distance actually is, we can check, will be the length of this. So it should be 52 subtract negative 53 meter. So it's 105 meter. So the total distance, the car traveled from A to B to C, D, E, F should be D1 plus D2. And if we add it together, it's 22 plus 105 meter, 127 meter. This is for the same motion from A to B to C to D to E, F. The displacement is negative A3 because by definition is final position subtract the initial position. But the distance the car traveled is different from the displacement. And for distance, you really need to find out all the segments of the movement, find out the distance of each segment, and add the absolute value, which is a positive number of the traveling of each segment together to find out the distance. So this is the subtle difference between displacement and distance. And we can represent the displacement using graph. So it's always the displacement is always final position subtract initial position. So see, this gives us displacement from A to B, and this gives displacement from B to C. So it's negative from B to C. Now let's discuss how to calculate the speed. So speed should be distance the car traveled divided by the time it takes, and the speed. So speed is distance over time. So for example, a driver starts from Atlanta, drive to St. Petersburg. The distance is 500 miles. It takes 10 hours. So the average speed is 500 miles over 10 hours, give us 50 miles per hour. Now for the same trip, from Atlanta to St. Petersburg, the driver actually take a side trip to Jacksonville before he drive to St. Petersburg. Now the distance is more than 500, which is 600 miles, but it still takes 10 hours. So the speed is 6 miles per hour. So this is speed. Speed is distance over time. Now let's look at velocity. How velocity is defined. Now as long as we remember what is displacement, final position subtract the initial position. The definition of velocity is very simple. Average velocity is displacement over time, the time it takes for the displacement. So we can try to calculate the velocity of the object move from A to B. Move from A to B, the displacement, final position, subtract the initial position, the final position, initial position, the time it takes, 10. So average velocity from A to B is 2.2 meter per second. Now we can pick any 2 points to find out what's the average velocity. How about we do the same? Let's pick this initial position. This is final position. So let's see. Final position 55. Subtract initial position 30. The time it takes 50 seconds. Subtract 0. We count from A. The time 0 second takes 50 seconds, and unit should be meter per second. So is negative 83 divided by 50 meter per second. So the number should be negative 1.66 meter per second. And this is how we calculate velocity. Now remember the definition of velocity is displacement over time. We can also represent find out velocity on a graph, which is position versus time. And by definition is that x over delta t, so it's just the slope. So the average velocity between A and B, we just need to connect A and B. We find the slope of the non-joining A and B on a position versus time graph. Now the same, if we find the average velocity between A and F, we need to join A and F, and we find the slope of the line that joining A and F. So this is how to interpret average velocity. Average velocity on a position versus time graph is just a slope of the straight line joining initial and final position. So this example is the displacement from A to E. The displacement from A to E. So the displacement is position of E, negative 37, subtract. Yeah, actually there's a mistake on this. It should be initial position 30, so the displacement is negative 67 meters. So we try to find the slope of this line joining A and E. Displacement negative 67. The time it takes is 40 seconds. Yeah, so the average velocity from A to E is negative 1.7 meter per second. And then what is instantaneous velocity that our car gives us? And for that, we need to take the displacement for a time interval divided by the time interval. However, we need to take a very, very, very small time interval that is much, much smaller than 1. So it will basically give us instantaneous velocity. So here, by definition, it gives us average velocity from 3 seconds to 1 second. That's final position and that's initial position. And now we need to just need to find a very small time interval. For example, the time interval from 1 second to 1.01 second, and then we need to calculate what is the displacement for this very small time interval and find out the time. So we find at about 1 second is instantaneous velocity is close to 47 meters per second. And of course, we can still take an even smaller time interval. Then it will be even more close to the instantaneous velocity. So on a graph, instantaneous velocity is the tangent of the position versus time plot. The slope of the non-tangent to the position versus time curve give us instantaneous velocity. And if you can take the absolute value of velocity, it will give you speed of the object. So the instantaneous value velocity can be positive 15 meter per second or negative 15 meter per second, which means the car is moving in the positive direction or negative direction. But the speed for velocity positive 15 meter per second or negative 15 meter per second, the speed are both 15 meter per second. And now we define average acceleration. Average acceleration depends on two quantities. First, the change of velocity. Change of velocity, which is final velocity subtract the initial velocity, and the time it takes for this change. So this is the time the car has final velocity v_up, the time instance. Ti is the time instance the car has initial velocity vi. So change of velocity vf subtract vi. The time it takes for this change is tf subtract ti. So the average acceleration is defined as change of velocity divided by time interval. It final velocity subtract the initial velocity divided by the time interval it takes for this change. So for example, the initial velocity of the car is 10 meters per second. It accelerates to 20 meters per second and it takes 2 seconds for such change. So the average acceleration change of velocity, final velocity subtract the initial velocity divide the time takes for that change, give us the acceleration, average acceleration is 5 meters per second square. Now the unit for acceleration is meter per second square. So if the velocity and the acceleration are in the same direction, then the speed increases with time. If the velocity and acceleration are in opposite direction, then the speed will become smaller. Now, if we have initial velocity is negative 10 meters per second, final velocity is negative 20 meters per second, what would be the acceleration? The acceleration is negative 5 meters per second squared by definition. So it calculates as final velocity subtract initial velocity, give us negative 5 meters per second squared. but we have initial velocity is negative 10, so we can see the speed increase from 10 meter per second to 20 meter per second, but it's still in the negative direction. And the SI unit for acceleration is meter per second square. We can do the same to find out what is instantaneous acceleration. For instantaneous acceleration, now we need velocity versus time graph. Velocity versus time graph, then we need to find out what's the slope of the line that is tangent to the velocity curve, give us instantaneous acceleration. Now let's talk about how to represent an extended object for 1D motion. For us, we just use dot to represent the position of the car. We pick one point in the car, and to be consistent, we use that point to represent the position of the car. Now for this one, this is the motion diagram, and each snapshot is taken for fixed time interval. So if the distance for each snapshot is the same, apparently then the average velocity would be the same. This is a constant velocity motion. For constant velocity motion is pretty obvious. We have average velocity equals displacement over time and constant velocity. So for any time, v is a constant and it equals average velocity equals v. So we can find out equation for constant velocity motion. For constant velocity motion, we basically only have one equation to use. Displacement equals velocity times time. So for constant velocity motion, displacement equals velocity times time. We basically have this one kinematic equation for us to solve the problems. And now for this one, apparently the velocity of the car is changing, is going faster, and this is it depends on what would be the change of velocity at each time interval. Now, in this particular example, this is a constant acceleration motion. The acceleration is in the same direction as velocity. Now, this one, in this particular problem, is also a constant acceleration motion. The acceleration is the same all the time. It's in the opposite direction of velocity. Now, a constant acceleration motion. Constant acceleration motion, so apparently A should be a constant over time. So at any time, acceleration is a constant. So if you draw it, acceleration and t, in acceleration versus t plot, we should have a line that is parallel to t because a should be a constant. It doesn't change all over at any point. It doesn't change. And then a is fixed. How about the velocity? So we know for constant acceleration, which means change of velocity should be this time acceleration times t. Because by definition, a is that v over t, and a is always the same. So that v is a times t. which gives us v is proportionate t and the proportion is a. So the slope on this velocity versus time graph give us acceleration, and the slope is a constant. So v versus t should give us straight line with a slope if a is not 0. So let's have our fundamental equation for constant acceleration motion. If we know the initial velocity of the motion, we know acceleration, we can predict what will be the velocity of the motion at any later time. It should be given by initial velocity plus a times t. And it's derived. Let's start from definition of acceleration. So this equation is definition of acceleration. And we just rewrite this is final velocity, initial velocity, time interval. We multiply t on both sides, right? We multiply t on both sides, it will give us this equation. Multiply t on both sides give us at equals v subtract v0. And then we can add a v0 on both sides, give us this equation. And we'll call this the first equation of constant acceleration motion. Let's look at one example. If the initial velocity is 2 meters per second, the acceleration is 6 meters per second square, what will be the final velocity of the object after 2 seconds? So we use that equation we just learned. Final velocity equals initial velocity plus at. Initial velocity we already know, 2 meters per second. Acceleration 6 meters per second square. T is 2, and the velocity at time t equal 2 is 14 meters per second. Now we can also have the average velocity for constant acceleration motion is initial velocity plus final velocity divided by 2. And so we can also have the displacement can be calculated as 1/2 initial velocity plus final velocity times t. And how do we know that? Because of what we have, so if you have a constant velocity motion, we have v, we have t. Then the displacement, this gives us constant velocity, right? The displacement is v times t, which also is exactly, see, this is v, this is t area under this curve. So we can kind of generate that. The area under v versus time graph give us the displacement. So the displacement for constant acceleration motion should be the area of this trapezoid, which can be calculated as 1/2, right? 1/2 v0 plus final velocity times this side t. This is for constant acceleration motion. We have this equation. for constant acceleration motion. So now we want to derive another very useful equation. We start from this equation we just derived, and then we substitute v using the first kinematic equation we derived here. This we call it the first kinematic equation. So we substitute v. We substitute the v. So this is our v, right? This is v. And put everything together. Put everything together, we find the displacement equals initial velocity times t plus 1/2 at squared. So let's call this one equation 3. And actually this one is equation 2. Call this one equation 3. The displacement of a constant acceleration motion, displacement of a constant acceleration motion equals initial velocity times time plus 1/2 at squared. And the interpretation, this is initial velocity. This rectangle times time is v0t. And 1/2 at squared, it gives this blue triangle. And this is at, this is t, so the area is 1/2 at squared. And we know the area under this v versus time plot gives us displacement. So this is a geometric interpretation of the equation 3 of kinematic equations. And this can be generalized and make a very more general statement. If you have velocity versus time graph, then area under this curve give you displacement. Now we can derive another useful equation. We just need to replace, we just solve for t from the first equation we have, solve for t. So we need to subtract the v0 on both sides and then divide it by a. We find out t equals final velocity subtract initial velocity divided by acceleration. Okay, we substitute t by the right hand side. And then we work out all the terms. We find displacement equals final velocity squared, subtract the initial velocity squared divided by 2a. And then we multiply 2a on both sides. We multiply 2a on both sides. We find this equation. We call it equation 4 for constant acceleration motion. So to summarize, those three equations would be extremely important for our calculation. Now we examine a special case of constant acceleration, which we call free falling motion. Free falling motion. A free falling object is object that move freely. There is no other force except gravity. So there's only one force acting on the object. And on the surface of the Earth, the acceleration of the object due to gravity is roughly 9.8 meters per second squared. So we can use the following kinematic equation to solve any free falling problem. Final velocity equals initial velocity is supposed to be plus at, right? But we know for free falling the acceleration is pointing down. If you choose up to be positive,